the video on triangle similarity part 2. What kinds of questions can I see? What are the uses? What's the purpose? So there are 3 types of questions that you could be asked dealing with similar triangles, just like in congruence. They're the same types of questions actually. Type 1 is asking whether or not 2 triangles are similar and often why. So example 1, are these triangles similar? And if so, by which of the 3 minimal conditions? So when I look at these triangles TSR and TEF, there are some side lengths given. I'm going to compare those. I'll check the ratios. And when I check them, what I want to do is compare the correct ones, the right corresponding ones. So in TFE, for instance, I have side lengths 7 and 8. In TSR or TRS, I have 21 and 24. The 21 is the shorter of the 2 sides, and the 7 is the shorter of the 2 sides that are given. So those are the ones. The 2 shorter sides are the ones I'll compare. The longer ones of the 2 I'll compare here. And the ratio is the same. There's no information about a third side. So probably I'm dealing with an SAS, although it's possible still that it could be a different one. But in fact, here it is an SAS because the angle between those 2 sides, this angle here, angle STR and angle ETF, those ones are vertically opposite and thus equal to each other. So those triangles are similar. This is by SAS. Are these triangles similar? And if so, by which condition? I can tell that I've got all 3 sides. So for sure, that's what I'm going to check to see if the ratio is the same in all 3. And when I do that, I'll check, let's say, the largest and the largest. So that reduces to 13 to 5 as a ratio. These ones have the same ratio. These ones have the same ratio as well. They all reduce to a ratio of 13 to 5. And so these are similar by SSS. It's not good enough just to have all 3 sides. I actually have to show that the ratio is the same for all 3 of them. Second type, asking which is similar. And that's a very common multiple choice question on a final exam. So which of the following is necessarily similar to this triangle LMN? And like in congruence, when we went through this, I'll go through them one by one, proving why one of them is correct. So in A, for instance, we have 2 sides and 1 angle. We'll see if the ratio matches. Also, just to situate things, this angle is this angle here. So we know which 2 sides we're comparing. The ratio of the longer sides, that's the 90 to the 28, reduces to 45 to 14. That's those 2. And the shorter sides, not equal. The 16 to 14, not the same ratio. So though we have 2 sides and an angle between them, the ratio isn't the same. That one is not similar. Next up, B. I have 2 equal angles. The side is irrelevant because angle is one of the 3 minimal conditions. B is already correct, but I'll just quickly show you why the other 2 would not be correct. In C, I have 2 sides and 1 angle, but it's not the angle between. So that's not one of the minimal conditions. And though there are 3 sides here, the ratio is not the same for all. So that one's out. And finally, asking to prove that 2 triangles are similar and then find a missing link. This one is probably the most difficult because the format is specific and there's an extra step in it. I'll show you what I mean by that. So show that triangles ABC and ADE are similar and then find the length of segment DE. That's the one that's missing there. So first up is to prove that the triangles are similar. Proving that the triangles are similar, I'm just gonna proving that the triangles are similar means following the same format that we did for congruence, a 2-column proof. But what I wrote here was that when we are comparing sides, be sure that you check the correct sides. So it is possible that the triangles can be flipped, rotated. Just because ABC fits inside triangle ADE, it doesn't mean that this side length necessarily corresponds to this side length on the same side. They could have been flipped. So when I check, I have to look at here, 2.6 is of these 2 sides that come down the slanted sides of ABC. 2.6 is the longer of those 2 sides. So the ones that form angle BAC or CAB. AC is the longer of the 2 sides. And similarly, AE is the longer of the two sides in AD and AE. So it turns out that they are on the correct side, but you have to verify that first. Okay, here I go with my proof. Statement 1 is that the ratio of AD, this entire length, that's the longer triangle, over AB is a total of 6, because I'm taking this entire length, 2.4 plus 3.6, over the side length AB. That is a ratio of 5 to 2. Those are corresponding sides. This ratio of AE, the entire thing, so I'm adding 2.6 plus 3.9 over 2.6, that is a ratio of 5.2, same ratio. An angle DAE and angle BAC, I name them in the same direction, both starting from the left side, because it turns out that the triangles are not flipped. Those are the corresponding sides. I should name them the same way. Angle DAE and angle BAC are equal because they're a common angle. They share angle A. And so those two triangles, ADE, I name them from like here, A down the shorter of the two sides and then across this side here, and I name it the same way here, A down the shorter of the sides and across. They are similar by SAS. And finally, what it actually asked me to do was to find the missing length. And that is the ratio of DE over BC. I know that the BC length is 2.8, but what I know is that that has to equal 5 over 2. I'm just going to quickly backtrack, because that was the ratio of the other corresponding sides. And in a similar triangle, which we now have proven that these two are similar, that ratio has to be the same for all corresponding sides. So that's how I can find the missing unit. I called it planes because there were no units. That's a callback from a previous thing that we talked about. And that is the end of part 2 of similarity.